Hello, and welcome again to the next installment of Lesson 6, which is the mathematics of network models. We're using this branch system as our initial example, and we're going to use the mathematics constructed from this to come up with the algorithmic structure that can be extended to larger cases. If you recall at the end of last episode, look at me. We had hit upon this case where this is the Jacobian. Here's the coefficient matrix that becomes part of the function, and this is the update scheme we want to employ. So now we're going to build a spreadsheet model to handle the various parts of the calculations. We'll build it specific to this problem, but it will become reasonably obvious that it's expandable to any problem that can be structured in the hydraulic modeling sense, and that there's the correct amount of equations and nodes. So let me escape from that. Let me bring up my spreadsheet model, and this will be an example. Quasi solver for hydraulic networks. Okay, I'm trying to do this from memory. I have many of these built in the past, and I'll do the best I can, and I can always refer to an example later. Let me go ahead and save a copy. I'll put it onto my desktop, and we'll get it uploaded to the server later. My network. I can't spell. Let's call it my network model. Now let's go through a little bit of remembering on what kind of components we're going to need in a model. We're going to have pipes. In our case, we have pipe AD. So let's call this pipe ID, or actually element ID. See why I'm doing that in a minute. So we have pipe AD, we have pipe BD, BD, pipe DC, and we have nodes D. So those are just names. We're not going to make any use of them other than to help us keep track of things. Pipes have a length. If we go back and look at the example, 5,000, 3,000, and 4,000. They have a diameter. If we look at our deal, it's 0.6, 0.8, 1.2, 6, 0.8, 1.2. If we knew what they were made out of, we would have a roughness, height, and so forth. We're going to leave that blank, but we'll build it in later. So there'll be a roughness, viscosity, and current value. Let's call it current Q. If we know the current flow rate, we can get the current Reynolds number, and we can get the friction factor. In our example, these are 0.015. We need to know gravitational acceleration. And let's see if the constants, only put it up here somewhere. We insert a line here. We'll have an initial guess. I'm trying to remember what else I need. Okay, if I know the friction factor, I can get the current. I'll change the current Q later. Current L factor. So L is, this equals 8 times the friction factor times the length times absolute value of whatever the current flow rate is, divided by pi squared times G times diameter raised to the 5th power. Oh, I hope that works. Okay. Now we need to make our node arc incidence matrix. And let me insert an extra column. This is mostly so nodes, pipes. This will be node D, and then there's pipe AD, BD, DC. D, D, DC, and D, and so the matrix is actually going to go in here. We'll have our B vector, which I called my right-hand side. We'll get to that in a minute. And so let's go ahead and write the balance equation for node 1. So it's 1, 1, minus 1, 0. If we look at our overhead, I'm literally building this. AD is equal to, this equals minus current L. This one equals minus the current L. This one equals minus the current L. We have to have these zeros in place because we're going to be doing linear algebra in Excel, and it detests blank spaces. Minus 1, minus 1, plus 1. And now we have to submit the right-hand side. So that first one's a 0 because HD is not involved in the node balance. But this first one is minus HA. So let's go look at our numerical values. So 70, 180. So minus 70, minus 100, and then the last one was plus 80. And there's where our guess vector goes. And so this is the AX vector, and I'm going to go ahead and just put a border around it so we know what's going on. Border around it so we know what's going on. This is going to equal transpose of our current vector I'm pressing Control-Shift-Enter. Let me go ahead and put my initial head there at 50. Okay, cool. So I'm going to call that the current X, and I'll call this initial X, and that's just to remind me that it's including both flows and head values. Okay, let's get my f of x value. So this is equal to matrix multiply of that matrix times that right-hand side minus that right-hand side. Control-Shift-Enter. Let's see if that makes sense. Let's just change some values of x. I don't know what the actual values are, but 12, 11, 10. It looks like it's automatically updating. If we could make this, looks like the second one bigger. Okay, it seems to be working the way I expected. I'm not going for any particular numbers. We're going to be automating this. So this is my matrix. That's my f of x vector. Let's surround it with thick box borders, and for grins we'll surround that with thick box borders. But this one we're also going to put some neutral value in there. All right, now we need our Jacobian. So our Jacobian matrix kind of has the same structure, but this is the Jacobian, and we've just determined if we study our development carefully, we'll see that the Jacobian associated with any of the node balance equations is just that value. So this equals that, and the Jacobian associated with any of the head balance equations is simply equal to twice whatever it is. Let me highlight some things here. And I need some other cool colors. Okay, the ones that are just highlighted in that light orange, those are all the head loss terms. And so the Jacobian of the head loss terms are twice whatever they are in the node arc matrix. The Jacobian of the balance terms is equal to itself. The Jacobian of the terms associated with the non-zero heads are themselves, and then this zero in this corner, that will grow depending on the number of node equations, but that's the Jacobian of 0 is 0. So that's my Jacobian matrix. I now want to solve this equation. I want to solve the Jacobian times an unknown update equals f of x of the right-hand side. So that's going to take a little bit of trickiness. If I do this right, Let me copy this equals that. See if it'll pick it up. Cool. And so this is going to be my xk plus 1 . Okay, so the linear system that's the negative of that thing times this unknown vector equals that thing. So this unknown vector is obtained by Jacobian transpose Jacobian. I take this matrix, invert it, make it negative, and multiply it by the right-hand side. So this is equal minus matrix inverse of that times that, and let me get the order right, M-N-U-L-T. So I'm going to do matrix multiply the inverse and so now we have initial update x. So this is equal to transpose of that minus current. See what went wrong. Now let's try a different way. Equals transpose of that minus that. There we go. So that's a single step. Now we need to insert some scripting to go ahead and automate things. Let's go ahead and put a few rows up here. And reset iteration. This equals if above equals 0, set myself equal to 1. Otherwise, set myself equal to self plus 1. We have to go in here and make a couple of changes. On Macintosh, you use preferences, use something similar. On that, we want to go ahead and allow iterations. You do manual updating. Choose OK, and it looks like calculate now is command plus equals. Okay, set reset to 0, do command equals. So this is an iteration counter. I'm going to go ahead and put that in red so I remember that. So I'll do reset to set everything, and then I'll just keep track of iterations. Currently it's set to do 100 iterations. Let's go ahead and go into one iteration at a time, because then we'll be able to see what's going on. Okay, reset iterations. And now we have to make, Okay, so this equals if reset equals 0, then use above, otherwise use below. And we need to force it to hold the correct column. Alright, there's my counter. Let's see, roughness doesn't matter, gravity. Okay, so the current Reynolds number is used for when we're going to compute friction factors. Viscosity will need that, and roughness will be if we're going to do a Darcy-Weisbach, a variable friction factor model. So as it is, okay, this should be a fairly generic solution tool. Let's check the correct answer. Should be, I'm guessing flow is going to go to the 70s. We should get heads at the intermediate value are going to be bigger than 70 and smaller than 80, I think. So we should get heads somewhere in the 80s. So this 50, we'll leave that as the initial guess. And let's go ahead and see what happens. Because if I've got this set right, we should be happy. And let's go ahead and hit Shift equals. Okay, so the first update is done there. Second update, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th. I have a mistake somewhere in the construction because it is diverging. So let me pause briefly. Okay, welcome back. So after a little bit of debugging, I had made a sign error in the update. So that's the same as before. But that's now dq, and so my new value of k is actually the old value plus this delta q term. And I had it as minus, so I had a sign error. I now believe I have it working correctly. I went ahead and pulled a bunch of constants out during the debugging. The rest is the same as before, so let me go ahead and hope that works. I think if I delete those rows, sweet, edit, delete those rows, we're now back to the system. So this column is I'm going to call this my delta x column. Okay, so it's still the result of the -1 times the inverse of the Jacobian times the f of x value. And then the update takes the old value and adds it to the delta x value, and then this is just it right here. So a single sign error was why it was not converging. We go ahead and hit this, hit our equal sign, and I want you to keep your eye on the f of x structure as we pound through. You notice the numbers are getting smaller. In fact, let's have some fun till the daddy takes my T-bird away. Let's format those cells. Let's let them have about 5 decimal places. We are done. We now have an answer. And the answer is that the flow in pipe AD is minus 0.046 meters cubed per second. The flow in pipe DB is 0.15, and the flow in pipe DC is 0.109, and the intermediate value of head is 81 meters. So if we go back to our original problem, and let me see if I can, let's be sneaky here. Let me see if I can capture this. I'm going to plug it onto my initial problem, and then we'll write okay, I found one other mistake. I forgot to multiply by the friction factor. So let's go ahead and start all over again. Reset to 1. This should now be correct. Looking at that right-hand side, and essentially we have a solution. And so now our solution is right here. Let's go ahead and capture that. Put our solution there, and you'll see why in a second. So it's telling us that the flow in that pipe is at 0.381. The flow in this pipe is 1.27, and the flow in this pipe is 0.89. And to check that, if we look at it doing by a different method, we have agreement here. 0.381, 1.237, 0.89, head at 81.6. Essentially the same values. Okay, so now we have a generic algorithm. Let's go ahead and shell out and look at a homework assignment and see if we can use this tool to solve a homework assignment. We'll take a problem out of a how-to manual from the reading. And show you the utility of what we've just built. Let's look at this 3 reservoir problem. So first we'll capture it. B and C. We will call the node center J, so reservoir A is going to have pipe AJ, reservoir B is going to have pipe BJ, reservoir C is going to have pipe JC. The node is J. That's the change there. The length of AJ is 900. The length of BJ is 800. The length of JC is 700. The diameters of all of those are unknown. 850 millimeters. So those are 0.85 meters, 0.85 meters, 0.85 meters. 9.8 doesn't change, pi doesn't change. And I don't know the friction factor, but I'm going to just 0.017. Okay, that's literally all we have to change. Hit that with a 0, hit that with an equal sign, hit that with a 1. Let's see what happens. So this is a new problem. That's it, that's good enough. So, not entirely new problem. I forgot to correct the right-hand side. Reservoir A is at 100. Reservoir B is at, Reservoir B is at 80. And reservoir C is at 60. we now have 2.6 cubic meters per second in pipe AJ, 0.31 in pipe BJ, and 2.98 in pipe JC, and the intermediate total head is 79 meters. Let's see what we would have gotten if we ran it in EPA-NET. I think the results are shown here. We may not be able to see them. So the EPA-NET had 2818 liters per second, so it's 2.8 meters per second. Ours was 2.6. That one was 335, which would be 0.3. Ours is 0.3. And the last one is 3154, which would be 3.15. We're a little lower here. What we can't see in this particular output file is I don't know what the head loss terms are. But let's go ahead and modify this so that we can actually calculate friction factors using the friction factor formula. So first we want to go look up our friction factor formula. Go to the online toolbox because we happen to know there's a friction factor calculator, and it won't work because it's an idiot. Okay, so there's the formula. So the friction factor that we want is going to be equal to sand roughness height. I forget what it is for this, but I'll just it can't be right. 0.12. Okay, so that should be 0.26 millimeters, which would be 0.0026 meters. And see if it will let me keep the formula where I can see it. So now I'm going to replace this cell with that formula. We have to calculate a Reynolds number, so I'm going to put ones there for now, and we'll go ahead and include a formula for that. All right, so our friction factor is equal to 0.25 divided by log of Ks divided by our diameter divided by 3.7 plus 5.74 divided by Reynolds number raised to the 0.9, and then that whole thing is squared. Okay, so it produced a number, and now let's start grouping terms so that we don't have unanticipated results. It's okay. It's everything in the log, and I want to get that all grouped. Okay, now I need a Reynolds number calculator. Let's go see what we need for that. Reynolds number is rho VD over mu, or VD over nu. So let's use the other version of viscosity. We'll go ahead and look up a water property. We want to use this 1e minus 6. 1e minus 6. 1e minus 6. 1e minus 6. You can see we're making our tool even more and more general. Okay, so I need velocity times diameter over nu. So current Reynolds number is equal to, give myself a row, velocity is equal to current discharge divided by pi times diameter squared. And it would be over 4, so 0.25 times. Should take care of that. Alright, so now my current Reynolds number is equal to whatever the value of velocity is times the diameter divided by viscosity. Okay, so we got friction factors, makes sense. Nothing else has changed. We've forced Reynolds numbers to be positive. Let's see what happens. Looks like I may have introduced a mistake. Velocity. Still not quite the same as the EPA net. Now they're using a different head loss model, likely. Roughness height, 0.26 millimeters. So that part's correct. The only way to make it anywhere closer to EPA net, the only other difference I can think of is viscosity. But the point is, we now have a fairly general model for a Darcy-Weisbach solution for solving hydraulic networks. Okay, so I'm going to conclude this video. There's going to be a substantial amount of editing, so you will never see it. We will go on to another example. But the key thing in this is the matrix, the Jacobian, the update. Quite simple. And we can actually make one more modification before I quit. We will automated updating. And it's done. Okay, I think that's pretty cool. And that's pretty much how EPA net works inside. I really do not understand 180 and 60, unless I'm solving a different problem. 180 and 60. That looks like a 6 to me. Just for fun. Just in case, let's see, shift. Yeah, no, it's different arithmetic. It's in the friction calculation. EPA net's calculating friction. Similar formula to this, but different. And since this formula is a correlation anyway, there's no guarantee. They're both good enough, and so we'll go with it. All right, that concludes this video.